Hi there, Haya. This is your lesson for Monday, the 22nd of March. This will be the last piece of content that we do before we start revising for an assessment. And we're going to be doing fields, electric fields, magnetic fields. Now, we have dealt with electricity, dealt with electrons, etc. And you have looked at magnetic fields before a wee bit, probably in second year or third year, maybe fourth year. So we're going to bring it all together and talk about fields. You have actually done fields before in gravitational fields, and you should be familiar a little bit about how gravitational fields work. So we're going to bring that in to help explain electric fields, magnetic fields. Okay, the pointer's not working. I can't get my pointer to work, so you're just going to have to try and bear with me as we go through this. So the first thing we need to learn is there are four types of particle, charged particle, that you may be asked, you're expected to be familiar with at higher. And if you're given anything else apart from these four types, then you will be given information on the question paper or in the question. Now, for each of these four, you need to be familiar with their composition, in other words, what it's made from, made of, what the symbol is, what type of charge it has, positive or negative, what its charge value is in coulombs, that's symbol Q, and its mass. So the first one is an electron. It's a single particle called a subatomic particle, has a symbol E with a little negative, it's negative charge, and it's minus 1.6 times 10 to the negative 19 coulombs. You will find that on the data sheet that you get along with any exam. And its mass is 9.11 times 10 to the negative 31 kilograms. Again, you'll find that in a data sheet. Now, a proton, single particle, E with a plus, so it's basically same charge as a electron, but it's positive rather than negative. It's positive and it has a much larger mass. Again, it's on the data sheet. That's 1.673 times 10 to the negative 27. Now, the beta particle and alpha particle are types of radiation. A beta particle is actually very similar to an electron. It's involved in something called beta decay, and it gets ejected from the atom, and it has the same properties as an electron. We're not going to go into detail where a beta particle comes from this time. We might go into it later, but it's same properties as an electron, so same charge and same mass. You get that from the datasheet. And finally, an alpha particle is made up of 2 protons and 2 neutrons, and those who do chemistry will know that's a helium nucleus, and it's given a symbol alpha. It's positive and it has quite a large mass because it's got 2 protons, and so it's not 2 protons and 2 electrons, it's 2 protons and 2 neutrons. I'm going to change that slide there. So again, it's the addition of those 2 particles, 2 protons and 2 neutrons. Okay, field lines. You would probably be familiar with field lines from your work in second year, and we're going to look at what field lines look like. Field lines represent force, so these lines represent the direction of the force, and the direction of the force is indicated by the arrow, the direction of the arrow. So if the arrow is going one way, then that's the force experienced. So for electric fields, the field lines represent what would happen to a piece of positive charge, for example, a proton. So at the top here, you've got a positive charge and a negative charge. The positive charge has the arrows coming out from it, and that means that any positive charge nearby will get repelled from the positive charge. The negative charge at the top, right there, the blue one, has all the lines going into it, meaning that it will attract any positive charge. You need to be familiar with the 2 at the top, which is one for a positive charge particle and the negative charge particle. You also need to be familiar with when they're opposites, so that one below it on the left, you've got a negative red one there and a positive green one. What's happening between them? You'll notice the lines are flowing between them, the arrow's going from positive to negative. And you need to be familiar with what it looks like when they're opposite. So the 2 positives there are opposite, and you see the arrows for the positive are going away, but they don't touch, they don't line up, and there's no field lines going between them. If it's a negatively charged, 2 negative charges, same field lines, but the arrows will be facing the other way. So you need to be familiar with all 4 of these. A particular type of field that we're interested in is known as a uniform field produced from charged parallel plates. So here is 2 charged parallel plates. We would use a DC supply. We'd charge one plate up to be positive, one plate up to be negative, and we'd have these straight field lines between the two plates. This is known as a uniform field, produced by two charged parallel plates. We're going to look at what happens when we put charged particles inside this electric field. You need to be familiar with the diagram here and the straight lines between them. So this is what happens here. If you've got a uniform field, this is a uniform field set up on the right hand side. If you put charged particles into that field, so the negative electrons, the little red electrons here, if they come in from the left and they already have a velocity, they will change direction. Positive protons come in from the left and they will change direction. So the positive protons in this example will get attracted towards the negative plate, and the negative electrons will get attracted towards the positive plate. If you just place the electrons or protons inside the field, they will move towards the opposite plate. So that's just showing you what happens if you put the charged particles inside them. So if you are applying a force to anything, then there must be energy to provide that force. So we're going to go back and talk a little bit about gravitational fields to help you understand where the energy comes from. So gravitational fields are similar to electric fields and can be used to explain the electric field behaviour. In a gravitational field, mass is pulled downwards by gravity. So all mass is pulled down. And if we want to lift mass up, then we need to do work. We need to provide energy to do that. And as you lift it up, the work done to lift it up gets turned into potential energy, gravitational potential energy. And that's proportional to the mass of the object, the gravitational field strength, and the height, mgh. If you then drop it, that potential energy gets converted into kinetic energy, turning that mgh into a half mv squared. So just showing you here, if you have a gravitational field on the right hand side of the formula, the potential energy gets converted into kinetic energy and allows you to calculate the speed of the particle or speed of the mass as it hits the ground. So work must be done to oppose the field, to lift it up, and if you release it, that turns into EK. So you get work turn into potential energy and then converting back into EK. So let's look at what happens inside an electric field. Very similar. If I take a positive particle here in an electric field, this could equally be done with a negative particle, just would have to turn alternate the way the field lines are, have a negative on the top and the positive on the bottom. But for a positive particle, work must be done to lift it or push it towards the positive plate. It doesn't want to be against the positive plate, it wants to fall back down to the negative plate. So work must be done to lift it up, and the size of that work depends on the size of the charge and the size of that potential difference between the plates. How much voltage you have across these plates. So the work done is proportional to Q, size of the charge, and the potential difference V. Now, if you then release the charge once it's in this example, at the positive plate, it will then fall back down towards the negative plate, converting that QV back into a half mv squared. So work done is converted into electrical potential. We don't have a formula for that just now. But then that work done equals your QV. So your QV equals electrical potential, and then that converts back into half mv squared. Very important formula for working out the speed of particles inside electric fields. So we can use this kind of property of the work being provided by the electric field to provide kinetic energy. We can increase the amount of kinetic energy of a particle. We can accelerate a particle by passing it through an electric field. And this is an example here of something known as a particle accelerator. We accelerate the particles by putting them inside the electric field. Now, on the diagram here, you've got initial kinetic energy on the left, and it passes into the electric field, and this electron will get accelerated towards the positive side, and it come out the other side with initial kinetic energy plus its gained kinetic energy, and the gained kinetic energy, not the total, but the gained is equal to what it got from the electric field. So with a half mv squared, it would be equal to QV in this example. So important, it's not the total EK, it's what you get from the electric field. It can come in with kinetic energy, but it can gain some kinetic energy from the electric field by using QV. Now we can use this, magnetic fields are also used inside particle accelerators and industrial particle accelerators. So we're going to talk a little bit about magnetic fields and then bring it together to talk about examples of particle accelerators. So what we need to know about magnetic fields is that they're similar to electric fields in terms of their field lines, etc. They have a north and a south pole, similar to the positive and negative sides of an electric field. And field lines flow from north to south, similar to we have when we go from positive to negative. Now, field patterns are similar, and any moving charged particles create magnetic fields. Now, this is, if you've got a permanent magnet, that's to do with the electrons inside the magnet. If you've got an electromagnet, it's because the electrons moving inside the wires. And the top diagram on the right there shows if you have a current, electric current passing through a wire, you have a magnetic field around about that wire. Now, we don't need to know much about that other than a magnetic field exists when you have electric current. Now, when a moving electron or current carrying wire is placed inside a magnetic field, this causes a magnetic field caused by the moving electron to interact with the magnetic field it's placed inside. So if you place a moving electron, which has its own magnetic field, inside another magnetic field, these two magnetic fields interact. They will repel one another or attract one another. If you put a current carrying wire inside a magnetic field, the moving electrons inside the wire interact, that create their own magnetic field, which then interacts with whatever magnetic field you put it inside, so repel or attract. And they all interact with one another in what's known as the right-hand rule, all 90 degrees to one another. You've got the magnetic field as your finger, the electric current as your second finger, and your force as your thumb. And it's quite important to try and think about that, your right-hand rule, when thinking about how you generate these different forces inside a magnetic field. And I'll show you in a second how all that comes together. So the force produced is perpendicular to the direction of the magnetic field and the direction of electric current, electron flow. This is often called the right-hand rule. So if you know the direction of the magnetic field, you know the direction of the current or the moving electron, you can work out the force experienced by that current, carrying conductor, or the electron. Now let's look at an example. So here we go, charged particle magnetic fields. When single charged particles are placed inside a magnetic field, the resulting force will cause the charged particle to follow a curved path. So we've got these, the positive charged particle and a negative charged particle entering this kind of region of crosses. That region of crosses is your magnetic field here. Now if I just skip down and discuss what the crosses mean. So the crosses use something known as an arrow analogy. So the cross represents the tail of the arrow, the back of the arrow. So in this example here, the magnetic field is going into the screen, into the page. If the magnetic field was coming out of the page, you would get dots instead of crosses. So the cross is the back of the arrow and the dot is the point of the arrow. So what we can then do is we can then say, well, the field in this example is going into the page. So field finger into the page. We can then see that if it's a positive charged particle, we can use the direction. In fact, let's do the negative one. The negative one would be the flow of the electrons. So if I use that, so if I line it up, then I know the force is going to be downwards because the thumb would be downwards. So the blue charged particle there goes downwards. Now, your finger, your second finger is only the flow of electrons. So if we have a flow of protons, we have to use the opposite direction, and my right hand won't do that. I can't flip it around to do that. So it's best to think about it in terms of negatively charged particles moving, and then just flip that direction to get your force if you need to. So this causes a curved path here that the electrons will flow, because the electrons or protons will flow because they already have a velocity as they come into the magnetic field. So that's the electric fields and that's the magnetic fields. Let's put them together and talk about the types of particle accelerator we have. There are 4 different types of particle accelerator: electrostatic accelerators, linear accelerators, cyclotrons and synchrotrons. I'm just going to give you a wee bit of detail on each, and you need to be familiar with the 4. The first one is electrostatic accelerator. This is what used to be used inside old televisions. You'd have a particle accelerator at the back, cathode and anode, and then the deflection coils there would use magnetic fields to change the direction of the electrons and send that little blue beam to different directions. So you'd have the cathode anode would accelerate the particle, and then the little red here, deflection coils, would change the direction of the electron. And when the electron hit the phosphorus screen, then it would light up. We don't really do this one as much, but you could get some kind of example. The next one is known as a linear accelerator. Now, there is no magnetic field in a linear accelerator. In a linear accelerator, it's about accelerating charged particles up to high speeds. So charged particles are accelerated by the electric field produced by large potential difference between metal tubes. and this one uses an electron beam, and you pass the electron beam down the centre between the tubes, and it's connected to an alternating supply. So if you look at them, the rings there, you've got P and Q, and the alternating supply charges up P, and then it charges up Q. So at any given moment, so P starts off positive, the electron gets pulled towards P, and then it flips to make Q positive, the electron continues to Q, then it makes the next tube positive, and it pulls it towards the next one, and the alternating supply is used to keep the electron flowing in the same direction. The process is repeated by alternating the voltage between increasing lengths of tube, and the tubes get longer because the particle is going faster in the same time, so it's got more time inside the tube, and it can accelerate it faster. We'll look at an example of this, a past paper example of this one near the end. You've then got a synchrotron. A synchrotron uses magnetic fields to keep charged particles flowing in a circle. So charged particles are accelerated by an electric field, produced a large potential difference between two metal Ds. So the D is either side of the diagram, shows you there, the D's on either side. An electric field keeps the particles spinning in a circle, and the potential difference between the D's, so that when in the D's, the path of the charged particle is changed by a magnetic field. The potential difference between the D's is alternated so that the charged particle are repeatedly accelerated as they cross the gap between the D's. So one side is always negative, one side is always positive, and as they pass through that gap in the middle, they accelerate. And the magnetic field is used to keep it flowing in a circle. And it's spin them up, they get them really fast, and then fire them at the end to increase it, to accelerate the particles. And the last one is known as a synchrotron. Charged particles are repeatedly accelerated as they pass through an electric field. Since the time taken for particles to complete one loop of the synchrotron decreases as their speed increases, the accelerating pulses must be synchronized. So they pulse in different particles, and they have to be synchronized to keep them going really fast. And it's, again, a magnetic field is used to keep it in a circle, an electric field is used to accelerate it, and this one is used to accelerate particles. Much larger scale than the other two. So let's look at a past paper question. I'm just going to run through briefly how you do it, and then you can take your time, pause it, and go through and work out the answers. So here we have a linear accelerator, same one that we looked at a couple of slides ago. An X-ray machine contains a linear accelerator as it is used to accelerate electrons towards a metal target. The linear accelerator consists of hollow metal tubes placed in a vacuum so there's no additional air particles to bash into. Electrons are accelerated across the gaps between the tubes by alternating supply. Calculate the work done on an electron as it accelerates from P to Q, so from P to Q. Now there you go, so work done is QV. Q would be the electron, 1.6 times 10 to the 19, and V would be the potential difference. It's given in the question, 2.5 kilovolts. So 2.50 times 10 to the power 3, and you get the work done in joules. Straightforward. Explain why an alternating supply is used in a linear accelerator. We talked about this earlier. Particle is always kept flowing in the same direction, or moving in the same direction. Forcing the particle and electron is always the same direction, or ensure the direction of the particle, it's all about direction, is correct. Second part of the question is, the electron beam is then passed onto a slalom magnet beam guide. The function of the beam guide is to direct electrons towards a metal target. Inside the beam guides R and S are two different magnetic fields acting on electrons. Electrons strike the metal target to produce high energy photons of radiation. Determine the direction of the magnetic field inside the beam guide R. So what's happening here is electron comes in and R is deflecting the electron upwards. So your magnetic field has to be either into the page or out the page. So if it's going to get forced upwards, then your thumb would be upwards. The electron beam would be that way. So I can't actually do that in my hand. There we go. That way. So my hand would be pointing towards me. So pointing towards me, electron is going to in my screen, the right. And then the force would be upwards. So your field would be out the page. I want you to try that with your right hand rule, and you'll see that it's coming out of the page. So out of the page would be your answer. State two differences between the magnetic fields inside beam guides R and S. Now S is bringing it down, R was bringing it up, S was bringing it down, so the magnetic field must be opposite direction to that in R. S must have an opposite magnetic field to that in R because it's bringing it down rather than up, so that you put that in. So magnetic fields are opposite in direction, but also it's bringing it down quicker. So if it's bringing it down quicker and it's a much tighter circle, the magnetic field must be stronger. so it's stronger as well. Two differences, 2 marks. Calculate the minimum speed of an electron that will produce a photon of energy 4.16 times 10 to the negative 17. So that's the amount of energy you want. That's how much energy you want in the electron. So really, you want that amount of kinetic energy to be hitting the metal target. So it's half mv squared, and if it needs that amount of energy, there's your energy, 4.16 times 10 to the negative 17 joules. Use a half mv squared because that's what turns it into an energy photon, and use the formula. Now, we'll be going over this in class this week. If you watch this video, great. I'll give you some questions to do, and we'll look at a homework, and you can work on that this week. Next week, we'll be starting to build a revision pack for you, and I want you to focus on that next week. So any questions you've got on this, please ask them in class, and we'll go over these slides this week.